let's talk about how we would actually set out to do a hypothesis test. And we're going to start out talking about there are a couple of different approaches to doing a hypothesis test. Our goal with both of these approaches is to decide whether the null hypothesis is what we call tenable, meaning we're not going to reject it, or whether we should reject that null hypothesis, which would make us think that the alternative hypothesis is likely to be true. In both of these approaches, we're going to set the alpha level up front, and then we're going to state the null and the alternative hypotheses before we start analyzing anything. Okay, so first approach, the p-value approach. So I am not going to talk about that in this particular video. And the particular textbook I happen to be using this time, we're not going to do it. But this is a perfectly valid approach to doing it. The general idea is we're going to calculate something called a test statistic. Okay, if we are interested in testing a hypothesis about the population mean, then our test statistic is going to be the sample mean minus the benchmark population mean. That's the value that we're testing that shows up in our null and alternative hypotheses. The x bar minus the benchmark, and we're going to divide by the standard error. Okay. So the sample mean minus the benchmark divided by the standard error. And in fact, that is going to be pretty much what we do all the time in all sorts of hypothesis tests, not just for the mean. Okay, let me write this out a little bigger in case it is hard for you to see. So we're going to take x bar minus our mu 0, and we're going to divide by the sigma, or the standard deviation of all the x bars. Okay, so that that sigma of the x bars is going to be our standard error. Remember, error here doesn't mean mistake, it means deviation from something that's expected or from the mean. Okay, so in this case, the sigma of all the x bars is equal to the population sigma, the population standard deviation, divided by the square root of n. Okay, and so then we're going to use the test statistic to calculate what we call a p-value, and usually this is done by some kind of technology, calculator, or much more often a computer. And then that p-value, p stands for probability, that we call that the observed significance level, is the probability of obtaining a sample statistic at least as extreme as the one that we have in our sample, if the null hypothesis is true. So given that the null hypothesis is true, what is the probability that our sample would be at least this far from the null hypothesis, at least this extreme? And then we call it a statistically significant result if that p-value is less than the alpha that we've already decided upon. Okay, and a statistically significant result means that we have an effect. Or an effect is the official statistical word. You might call it an interesting difference, something that we're digging into and we're trying to figure out if it differs from something else. Okay, if the p-value is less than or equal to the alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. So basically we compare the p-value that we get from our sample, we compare that to the alpha. Okay, and keeping in mind what we've talked about before, we can't ever prove that the null hypothesis is true. We don't accept it. The closest we can come to that is to conclude that there's not enough evidence to reject it. Now, the critical value approach, which is what I'm going to use here. Okay, so we want to figure out the rejection region, the non-rejection region, and the critical value. And by critical values, I mean of the test statistic. And so that'll be the same test statistic I mentioned a moment ago. Same test statistic, whether we're using the p-value method or the critical value approach. So the rejection region are going to be the values for the test statistics that cause us to reject the null hypothesis. The non-rejection region are the values for the test statistic that don't have us reject the null. Okay, and the critical values are going to be the values that separate the rejection region from the non-rejection region. Okay, so let's look at this little sketch. Okay, so the most common type of test is the two-tailed test. So I'm in the two-tailed test, our rejection region is going to be at both ends. So basically what we have here is we're going to put half the alpha in the left tail, and we're going to put half the alpha in the right tail. Okay? And so then the shaded area is going to be the rejection region. So that is going to be, we're going to reject H0, and then this way we are going to reject H0, and then in between here is going to be our non-rejection region. Okay, so then where the color changes, this is our critical value. So we're going to call this one Z alpha over 2, or it could be T alpha over 2 if we're doing a t-test. Okay, the concept is the same either way, and then in that case then these will be negative versions of those. Okay, so remember that critical value Z alpha, whatever the subscript is, in this case alpha over 2, that represents the area that's to the right for a positive Z value. Okay, so if that alpha over 2 happened to be 0.05, then this will be Z.05. Okay, so our critical values are the areas where the color changes. Okay, let's look at a left-tailed test. In a left-tailed test, all of our alpha goes into the left side, so we don't split it. And you can see from the picture why we call this a left-tailed test, or a one-tailed test instead of a two-tailed test. Okay, so here this value is negative, so this is going to be negative Z alpha or negative T alpha. And then our right-tailed test, all the area goes in the right. Guess how much comes in over here? Alpha. So we don't split the alpha. It all goes into one tail. Okay, that's why we call it a one-tailed test. So here this time we have a positive Z alpha or a positive T alpha, depending on what kind of a test we're using. And so in this case, our rejection region is going to be everything all over here. And then our non-rejection region is this side. And in this case, of course, where am I going to put it? Let's put it right here. This would be non-rejection this way. And then rejection over this way. So basically, if we end up in the shaded area, we're going to reject H0. If we don't end up in the shaded area, we are not going to reject H0. Okay, so our critical values, these are our critical values. In the two-tailed test, we've got 2 of them. In the one-tailed test, we've only got 1. Okay, so basically what we're going to do is we're going to calculate the test statistic, we're going to compare it to the critical value, we're going to look and examine whether we fall into the rejection region or not. And that's going to tell us whether we reject the null hypothesis. Okay, so how do we find the critical values? Okay, so we're going to start off with what we call a one mean Z test. Okay, so here we're going to be testing a hypothesis about one population mean. So it could either be a two-tailed test or a one-tailed test, either left-tailed or right-tailed. So when we're going to use the z-test, meaning our critical values are going to be z-values, it's going to be when our population standard deviation is known and our variable under consideration is normally distributed. And here's our test statistic. This should look familiar to you. Remember that our z, so if we have a z-score for an individual here, okay. Individual, it could be a person, one data point. Could be a person, a plant, whatever you're measuring. Okay, so that's going to be R. We're going to do X minus the population mean divided by the population standard deviation. Okay, and then the z-score for the mean of a sample, remember, is we're going to do x bar, because this time we're doing the mean of the sample instead of the individual value, minus the mean of all the x bars divided by the sigma of all the x bars. And remember, how do we get those? So this is going to be x bar, the mu of all the x bars is just the mu, and the sigma of all the x bars is going to be sigma divided by the square root of n. Okay, and so basically what we've got here when we do our z-score is we're subtracting in the numerator, we're using mu0 is what we're subtracting from the sample mean. So basically, here's how I remember this, and this will be true for any hypothesis test. It doesn't matter whether we're doing z, whether we're doing t, whether we're doing a single mean, two means, a population proportion, two population proportions, any number of other things. To get the test statistic, what we do we basically subtract what we're comparing, and we're going to divide by the standard error. And so now when we do different sorts of tests, we're going to be subtracting different things in the numerator, and there's going to be different ways to get our standard error depending on what type of a test we're doing. But the general layout of this is always the same. We subtract whatever we're comparing and we divide by the standard error. That'll really help you remember things and keep things organized in your mind. Okay, so that's basically our test statistic. So once we calculate the test statistic for a particular sample, we need to compare it to the critical value. So let's make sure we know how to get the critical value. Okay, so let's find the critical value for a two-tailed z-test with an alpha of 0.01. Okay, so the first thing I'm going to do is I'm going to draw my picture. Doesn't have to be pretty, it has to look just generally like a bell-shaped curve. Okay, and it's two-tailed, so that means we're going to shade both tails. So like this, okay? And then, how much am I going to put in each tail? Well, because there's two tails, I'm going to cut the alpha in half. So that's going to be 0.01 divided by 2, which is going to be 0.005. Okay, and then on the other side, same thing. The alpha over 2 is going to be 0.005. Okay, so what we want to find is this value here. This is where the color changes. So I'm going to call this z.005 because that's the area to the right. This one over here is going to be negative, so it's going to be the negative of z.005. Okay, and so what we need to do is we need to go to the table and figure out what this is. Okay, so I'm going to go to our particular table, keeping in mind as we do this. Okay, so if we want to find z.005, Okay, so what do we need to do? We need to figure out that the area to the left of z.005 is what? 1 minus that 0.005, which is going to be 0.995. Because remember, the area under the whole curve has got to all add up to 1. Okay, so if the area, that little shaded area to the right, over here, if all this is 0.005, then the rest of it's got to be 0.995. Okay, so what I'm going to do is I am going to look up area equals 0.995 in the z table. And then we're going to figure out what this gives us. So let me go to my z table. Okay, so I want to find an area of 0.995. So that means I need to go to the positive portion of the table, and I want to get as close as I can to 0.995. So I am floating around here in this table. Notice I didn't say a z-score of 0.995. I said an area of 0.995. So the areas are in the bottom of the areas are in the body, the main part of the table. The z-scores are on the left column and the right, the row across the top, right? So if I am looking for area equals 0.995, so I'm looking here, so I don't know if you can see my little yellow cursor, 0.9927, 9929, I'm getting close, 9945, 46, 9949, and then do you see how it looks like we're halfway in between those two? So what z-scores do those give me? So here we've got a 2.5, right? And then if we come up to the top, we have the 0.07 and the 0.08. So what we really want to be is we want to be halfway in between the 2.57 and 2.58, right? Does that make sense? So okay. So I am actually just going to undo all my yellow markings so that they won't be there when we come back to this table. Okay. So now we go back. All right, so we go back to where we were. Okay, so my area of 0.9949 corresponded to a z-score of 2.57, an area of 0.9951 corresponded to a z-score of 2.58. Okay, so if the area that we wanted was real close to one of those and further away from the other, we could just pick the closest one. Since this one looks like it splits the difference in half as far as we can tell, we should just go in between. We're going to split the difference, we'll go in between. So one way to split the difference is you could just add those two z-scores together and divide it by 2, basically to average them. Sometimes if you are trying to split them in your head, it will be easier to see if you add a 0 on the end like that. And so then you can just ask yourself, what's halfway in between 570 and 580? 575, right? So that means that our critical value is z, and I'm going to put a little subscript here, 0.005 equals 2.575. Just fixing the handwriting. Okay. There we go. And so my critical values, so I'm going to go put those on my picture. This is going to be 2.575. And now on the other side, what's that going to be? Negative 2.575. So if somebody asks me to write down the critical values, there's actually two of them, and I want to make sure I get them both. And let's label them properly as well. So z.005 equals 2.575, and then negative z point negative z.005 is equal to negative 2.575. So there we go. That's how we find the critical values. Okay, let's do another one. This time we want to find the critical values for a right-tailed z-test with an alpha of 0.10. And you should never do any of these. Even if it didn't ask me to reject the region, to sketch the region, I would sketch the region, because otherwise you're going to lose track of where you are. Just always sketch it. It doesn't have to be a pretty sketch, and it'll only take you like 5 seconds to do it. Okay, so right-tailed test, that's going to come over here, and all the alpha goes into this one tail. So this time we don't split it in half. We have a one-tailed test. Okay, and so then what do we label this color change point, or critical value? This is going to be z.10. Okay, so my alpha is 0.10. So now my area to the left is going to be what? 1 minus 0.10, so 0.90, right? And so then what I'm going to do is I'm going to look up area equals 0.90 in the z-table. And you notice I say area here, and I actually make myself write area, because if you just write 0.90, you're going to be really, really tempted, I promise you, to think of the 0.9 as being a z-score instead of thinking of the 0.9 as being an area. That's an extremely, extremely common mistake. And yes, it can happen to you. Okay, so then what we're going to do, so now we go back to our table. We want to get as close as we can to an area of 0.90. Okay, so once again, I'm going to go down to the positive version of my table, and I'm going to look for 0.90. Let's see how close we can get. Okay, I'm hovering my little yellow cursor, 8810, 8997, and 0.9015. This one is closer. If you can't do that subtraction in your head, just look and see which one of these is closer to 0.9. This one is 0.003 units apart. This one is 0.015 units apart. And since it seems to be much closer to one than the other, I'm going to just pick that particular z-score instead of going in between them. But if it was kind of halfway in between, I would split it, and it still won't be exact, right? Because all of these are rounded to 4 decimal places. So we're estimating. There's an awful lot of estimating that happens in statistics. Okay, so what does that give me? 1.28, right? Do y'all see that? Now, if you're alert, another thing that you can notice is, remember how we subtracted 0.1 from 1 to get the 0.9? So what if we looked up 0.1 in the table? For that, we're going to need to be over here on the left. But remember, the z-table is symmetric, so you actually can do that. So if we wanted to look up 0.10, area. Let's see how close we can get to an area of 0.10. .07, 0.08. .1. So do you see how that looks really, really close to 0.1? And what's my z-score? Negative 1.28. So negative 1.28. So that would be the area on the left. So the reason that works is because the normal distribution is symmetric. So really, if you just lost one half of your normal table, you should still be just fine. You can figure out everything with the other half. Okay, so once again, I'm going to undo these so we can keep a clean table. And let me undo these as well. Okay, and now I'm going to come back. Okay. And so we end up with my area equals 0.90 gave us a z-score of 1.28, right? So my critical value then, I'm going to put this over here. Z.10 is equal to 1.28. That's my critical value. Okay? Alright, one more. Okay, critical value for a left-tailed z-test with an alpha of 0.05. So once again, it's just one-tailed, so I put the whole alpha into this side. Okay, and so then I'm going to label this where the color changes. This is Z.05, except this one is going to be negative because we're on the left side, right? Remember this whole thing, if this is a standard normal curve, it's centered around 0, so the stuff on the left is negative and the stuff on the right is positive. Okay. So now what are we going to look up? Now we're going to look up area equals 0.05 in our table. And so that is going to get, let's go do it, area equals 0.05. Okay, so this time I actually want the negative half of the table, right? So how close can we get to 0.05? 485. Ooh, okay, 0.0495, that's really close. Ooh, 0.0505, that's really close. Do you see how it looks like we're about halfway in between again? So once again, I'm going to split the difference. So let's see, what do we end up with? We end up with, here's our negative 1.6, right? And then halfway in between those two guys. Okay, so this first one's going to give me negative 1.64, and then the other one negative 1.65. So once again we split it. It may be easier to see if you add a 0. What's halfway in between 640 and 650? 645, right? So my critical value is Z, I'm going to call this negative Z.05 equals negative 1.645. And I'm also going to write that on my table. So that is how we would find critical values using the normal distribution.